Welcome everybody. Session 3. What are your questions, comments, anything? You know what class 3 means? Homework 1 is due. You should have all known that. If you need any extra time, that's fine. A couple people pinged me already. Like I said, try to stick roughly to the schedule, because when I post sample solutions, I don't like to do that till at least the majority of them are in. But you can have a little bit extra time if you need it. So especially for the startup, the first one or two. So so if you're wondering, yes, you can have a little bit extra time, but just try to get it in as soon as possible. Okay. And I'll start looking at those later this week, and everything. Like I said, everything is on Blackboard, so your grade will show up on Blackboard. Post your homework on Blackboard, and that's how we'll manage it. Okay. Any other questions from last time? Or remember, start thinking about your project. You can work individually. You can work as a team. Pick from the list I gave you, or make a proposal for one that you're interested in. I'll take a look at it. So I'm pretty flexible there as well. Okay. All right. So let's tonight again. I would really continue from where we left off last time. We're going to get into a couple topics tonight. We're going to finish talking about some of the non-functional requirements, and then get into problem framing. And this is going to be the topic of your homework 3. So that's coming up tonight as well. Okay. Has anybody heard of the term WICKED project? Does anybody know what a WICKED project is? That's going to be our first topic. It's actually a term, an engineering term. It's used in the requirements area. I come from the Northeast, from New England, Connecticut, and up there they use wicked as an adjective to describe many things, like it's wicked cold outside, or it's wicked this. It's, so it's a common adjective used in the Northeast. I don't use that anymore. Now they've been down here so long. But that's not what we're talking about here. We're talking about a different type of wicked problem. A wicked problem is a problem where you'd like to know the requirements to this problem you're trying to solve, but unfortunately you don't even know enough about the problem to even be able to describe it well enough. So I want to give you an example, and some of you are too young to probably, or not probably, most of you are too young to remember when we landed on the moon way back in the 60s. Yes, I was alive then, and so yes, I'm older than you. But let me just, in case you never knew that, let me describe what that was all about. So we were in the middle of a Cold War with the Soviet Union, and we were both countries were involved in a space race. We were trying to find a way of landing a man on the moon, and it became part of a political statement being made at the time, and so both countries decided to go pursue this. Russia the Soviet Union got into orbit first. They launched a small little satellite called Sputnik, and that was circling the Earth, and it was panicking everybody in the U.S. because they thought that, well, if you can put a satellite in orbit and fly over the United States, well, then the next thing would be just you put a bunch of bombs on the satellite and then drop them over the U.S. There's nothing we can do about it. So everybody was all panicked about this whole thing. It became known as a space race, and well, we eventually caught up. We started getting serious about putting a man on the moon, and again, it was primarily a political statement to see whose technology was better. And around that time, it was when we first formed NASA as an agency, and they'd been around for a few years, but we actually commissioned them. Kennedy, President Kennedy at the time, made the famous statement that he was talking at Rice University, which is down in Houston, and made a statement about the space race and made the famous comment that by the end of the century, so he put a constraint on it, right? By the end of the century, time constraint, right? We shall, put a man on the moon and return him safely to the Earth. High-level statement, a high-level requirement statement. But now at that time when he said that, do you think that we had enough to generate a big, thick requirements document for how to build a spaceship and fly to the moon and back? No. As a matter of fact, we really had no idea how to do that, okay? So what we had to do is we had to start investigating the problem. We had to go find out more about the problem. So it wasn't like what we were talking about the last couple of classes where we could just, we can summarize the problem, do a root cause analysis, and know exactly what we had to go solve. This one was something where we didn't even really understand the problem, and so we had to go off and start doing some investigation. The first thing we had to do, let me go down to the desk camera, was we had to confirm that we could actually put someone in orbit. Okay, there were a lot of things we didn't know about, or maintaining somebody in orbit. When you're in orbit around the Earth, you're essentially in a controlled free fall, right? If you don't have the right angle, you're either going to come back into the Earth's atmosphere and burn up, So if you're circling the Earth, and if you're not at the right projection, you're going to fall into the Earth and burn up, or you can start bouncing out into space and go out into nowhere land. So there's a lot of mechanics associated just with staying in orbit. We didn't know whether you can sustain life in orbit, right? Things like this. And so we had to solve that or understand that problem better. And so what we did was we built a spaceship to do this, a rocket. We actually we called that part of the program Mercury. If you remember Project Mercury back in those days, that rocket was built not to go to the moon at all. It never would have made it to the moon. It was built for one reason only, and that was to be able to get someone into orbit and to understand that problem better. That was really all it was built for, right? It wasn't powerful enough to get us to the moon and back. Okay, and we did that. So one of the big requirements, or one of the things we were trying to solve or understand out of this first phase, was trying to just understand what's involved in orbital mechanics. We need to understand that. So we built this rocket. We went off. We understood that problem more. What did it do? It allowed us to understand some of the requirements better about what it took to keep someone in orbit, orbital dynamics, life support systems, and things like that. Okay. Then what we did is after we solved that problem, right around that time, we remember. Okay, so we have Earth here, we have the moon out here. There was a couple different ways you can get to the moon and back. One way was you build one big ship, and that big spacecraft lifts off, it flies all the way to the moon, it lands, it takes off, and it flies all the way back to the Earth. That was one way of doing it. The second way was having a separate, smaller vessel to land on the moon, and that's exactly what we ended up choosing, right? Remember, we had something called the command module, and then we had something called the lunar module, and the command module was what orbited the moon, and then the lunar module is the little thing that separated, went down, and actually landed on the moon, and then it took off from the moon, and then it docked with the command module, then flew back, right? Well, because we made that decision, we now we chose this one right here. That led to what's called, and we'll talk about it here a little bit, a set of derived requirements. What were the new derived requirements that we needed to build in order to support this decision we made? Well, one of the key derived requirements, or new requirements, in other words, it's not necessarily customer imposed, but something that we have to do anyway to solve the problem, it was space docking. Okay, now if we're going to take this lunar module and dock with a command module, we had to understand high precision space docking. And so part of the second phase of the operation, we built another spaceship, really another kind of rocket and system That one, if you remember, that was codenamed Gemini. Okay, and Gemini it solved a couple things. Again, we're going deeper into the problem, trying to understand the problem a little bit more. Gemini really tried to accomplish two things. One was, kind of high precision space docking. Okay, and if you remember, again, if you maybe see videos on some of this, they were trying to dock a couple different spaceship together, and it's a very high precision task. It requires this little joystick, and you gotta navigate your way in. If you don't get it right, you can bounce off each other. It can become a real big issue. And then the second thing was, if we're going to really go from the Earth all the way to the Moon, several 100,000 miles, we're more than likely we're going to have to repair something. And so during the second phase of the operation, they also is when we started performing, if you remember, those spacewalks, those tethered spacewalks where the astronauts would come out of the spaceship and wander around, mainly in case they had to go external and fix something. So they had to go solve that problem and invent new ways of doing that, et cetera. Okay, so we made this major decision. We understood orbital mechanics. We went off in life support. We went off and solved high precision space docking and spacewalks. We still haven't solved the problem. We still haven't put a man on the Moon and returned him safely to the Earth. But we understand a lot more about the problem now. As a matter of fact, some of the orbital mechanics and life support we improved during the Gemini program. And then we went on to really phase 3. And phase 3, if you remember, we called that Apollo. And that actually, what it did is it built or improved on steps 1 and steps 2. So it improved on all those things, and then actually was the ship that landed on the Moon and then back. So what did we do? So what was the approach here? We didn't understand the problem. I mean, we know what we wanted to do, but we really didn't understand how to do it. We couldn't solve the whole problem at once. And so we had to kind of break it into pieces, learn more about the problem before we finally were able to, get all the way there. So that was kind of the approach with our space program. And this, this was done in the 60s, and very good engineering, case study for what do you do when you don't really understand how to solve the problem. So wicked problems are kind of like that. And so these next couple slides are just kind of summarizing what I just discussed. So you've got them in your notes if you didn't take any notes. Okay. So now, how about what's an example of a more modern wicked problem? Can you think of a problem now where it's so complicated we don't really know how to solve it until we actually start getting into it? We actually start getting into the trying to crack the nut on the problem. We learn more about it. We change what we're doing a little bit, and we eventually figure it out. One of them that I can think of that's pretty significant is you heard a lot about this recently in the news, but if you've ever probably seen on TV some of the disaster warning systems. Now, these systems are meant to detect things like earthquakes, not react to them or warn when an earthquake is happening, but to be able to predict an earthquake. So earthquakes. Remember the tsunami. Remember those disasters, tsunamis, being able to, again, not warn when one's coming, but almost be able to give you much more warning ahead of time to be able to take precautionary steps. Well, these disaster warning systems, we learn more about the problem by getting more into them, by experiencing some of them, learning more about them, and then building a better and better system. This is another system where someone didn't just say, "Oh, okay, yeah, you want to solve disaster warning? Yeah, I know how to do that. We'll write up the requirements, and no, it's a lot more deeper than that." And there's more and more systems like this that are being built as software becomes more and more, large and complex. One of the other ones that we're trying to solve today, and you actually have a project on this, is autonomous vehicles. We know a little bit more about this, and we're starting to solve this fairly aggressively now, but for about 20 years, autonomous vehicles were being studied and looked at, and we're learning more and more about what technology we needed for these things. Now you're actually seeing some of this start to accelerate, and I think I mentioned this earlier, but in about 10 years, you're really going to start to see, I think I heard this week Cadillac, I don't know if you heard this, Cadillac just announced in the recent auto show that they are going to have a semi-autonomous vehicle in 2015. What that means is they're going to be able to, instead of going into cruise control like you do today, you'll be able to go into cruise control, but essentially take your hands off the wheel, and its various radars and sensors will keep it on the road by looking at the surrounding objects and the lines in the road and stuff like that. So not fully autonomous. I wouldn't trust it. I wouldn't go to sleep, but definitely kind of a semi-autonomous vehicle. So they're coming. We're cracking that nut as well. So all these can be considered, wicked problems. Okay, so a problem that is hard to understand and define until you start getting into solving it. Okay. Okay, I want to talk a little bit more. I got a few more slides on just these non-functional requirements, and then we'll get into again this next topic on problem framing, which should be a majority of the discussion tonight. But let me go through these quickly. I mentioned before how important it was to have quantifiable requirements instead of just saying things like it's got to be usable, it's got to be fast. So we talked about that last week. This is just kind of, again, re-emphasizing that. I think your homework too asks you to look at some requirements that are pretty vague and be able to identify where they're ambiguous and be able to offer a better way of describing a requirement. Oftentimes the ambiguity comes because they're not quantifiable. And I really think one of the most important things, or one of the most effective tools to verify, we're going to talk more about this when we talk about requirements validation, is to actually try to write a test case for that requirement. And you'll learn pretty quickly whether the requirement is phrased properly or not, because when you're a tester trying to actually test it, you have to know the pass-fail criteria. So it's a great way of doing validation. We'll talk about that later in the course. Now, there are some times where truly you don't know what the number should be. I'll give you an example. Let's say somebody comes to you, you're a contractor, and a customer comes to you and says, we want you to build this IT system for us, and it's got to be able to support 1,000 users, and it's got to have a certain response time for those users. Let's say 10 milliseconds per HTTP request, which is kind of a normal proxy response time for browser request. You say, okay, you go off, you study that, 1,000 users, I've got this kind of hardware, I've got this software, this operating system, this network, you kind of roll it up. We'll talk a little bit more about how you do that later on. And you decide that, okay, to meet 10 milliseconds, we're going to have to go out and buy this kind of hardware and this kind of software, and we'll piece it together, we'll make it work. Okay, now, if the customer is not knowledgeable about that number, 10 milliseconds, what if what if someone told them some false piece of information and instead they said 1 millisecond, okay? And now you have to come back and tell them how you're going to meet a requirement of 1 millisecond. Well, 1 millisecond may mean that they've got to buy a supercomputer, to get that kind of response time with 1,000 users. So suddenly, what happens to the cost of the system you're proposing? It goes up considerably, right, to meet that requirement. So in some cases, what you want to do is be cautionary. You want to say, you know what, I don't really know, if you're the customer, I don't really know what the number should be. I want you to help me with this. Okay, so let's take a look at what that means. There's this concept called open metric and open target. And normally it applies to these non-functional, again, sometimes we call them quality requirements. By the way, I'll use those interchangeably. If I say quality requirement, it's kind of the same thing as a non-functional requirement. We talked about the need to have these numerical targets. The open target approach is where so you're the one that's going to build the system. You're going to ask, you're the customer. You're going to ask the supplier, the one building the system, to specify what they think they can do. So, you know what? You tell me what you think you can do. I think it should be 10 milliseconds. You tell me what you think you can do. So you ask them to tell you, and that's an effective approach when you've got a competitive bid out. The customer, we can tell you what the expectation is. So if I'm the customer, I can say, I expect 10 milliseconds, but you know what? Tell me what you think you can offer, given these other constraints. Okay. Open metric. I've got some examples of this. Open metric. The customer doesn't even know how to measure that aspect of the requirement. You know what? Mr. Expert, you tell me, because I have absolutely no idea. I've got to build this for my company, but you know what? I don't even know. Can you please tell me? I know that sounds a little bit odd, but it's actually an effective approach. So if you go to this slide here, there are some cases, I've got a few example requirements here, where you can't specify the quantitative value because it's based on something that's well known, like a physical limit. So for example, this one, the toll booth system shall detect speed violations and take a photo of the vehicle within 0.45 seconds. So you've all driven through these toll booths, right? And you've seen the pictures flashing. That's based on relatively simple calculation for what they think the maximum car speed could be, how long it takes the sensor to detect the car going through the toll booth, and how quickly it takes to activate the picture, so that if you don't pay your fine or toll, you get that thing in the mail with your license plate clearly, shown on the camera photo. That's about 0.45 seconds by the time you enter the front part of the sensor detection system. It's a physical limit based on speed. You can calculate it, and for cases like that, there's no reason why you should not put a quantitative requirement or into the quantitative value into the requirement like this. Okay. So in that case, there's no real excuse. You should not just say you should take a photo of the vehicle as soon as possible. That wouldn't work right. Now, how about this next one? The conference room reservation system shall compute some kind of occupation forecast. So this could be something in large companies. Sometimes you actually see this being done. They'll actually compute forecasts based on past history of when certain conference rooms will be occupied, and give reports back on which ones have maximum use, least use, et cetera. And you say forecast within blank minutes or seconds. That's an open target. That basically says, give me what you think you can do, okay? How about this one? The supplier shall specify the forecast accuracy, okay? So this one is, worded slightly different. Up here at the open target, it's okay to say, I expect this, you tell me what you can do. The one below, open metric, that's more of the, you know what, you tell me based on some criteria, in this case, forecast accuracy to similar hotels, what you're going to propose. And that can be based on some set of constraints that you give them, like not to exceed. But you ask them, that's more of a, I don't know, you tell me, okay? In either case, it's okay to leave that open, that's why they call it open, leave it open to the supplier, the one that's building the system, to come back to you. Now, you don't want to do this for every requirement, but for those where it may have an impact on cost, delivery time, things like this, you can leave it flexible, okay? I think I've got, okay, so yeah, so I think I've got some other examples coming up later. But keep that in mind. So open target, you can ask the one building the system, the supplier, to specify the target. Open metric, you ask them to tell you what is the best in class based on metrics that they collect for other systems that they build. We actually get this a lot. We get, in networking, we get asked a lot by customers to specify what we think we can do as far as performance, and I think I mentioned a couple examples last class, like packets per second, security packets per second, things like this. we get asked this kind of thing a lot, and we specify what we think we can do based on certain conditions, okay? Does that make sense? Okay. There is also cost and benefit of quality or non-functional requirements. Again, when you're looking at something like my example response time, it's actually, the cost benefit needs to be understood. And this is an area where the requirements engineer actually has to do some real engineering. They can't just, again, they can't just talk to someone, regurgitate what they said, and go tell the engineers. In some cases, they actually have to do some real work. What is that cost-benefit curve? Who's going to figure it out? Who's going to work with the customer to determine that? Now, as a requirement engineer, you may go back and talk to your engineering team, but ultimately you have to communicate that set of data back to the customer. As you know, if the response time has to decrease, think response time meaning I ask for something on the web, I get a response back, that is going to be more expensive. Obviously, right? Okay. If I can decrease the response time, users can save money. What is that going to look like? Oftentimes, what you'll end up with is actually let me make sure I don't have this in my notes for you. Okay, I think I left that out of this. Basically, what it's going to look like is the following. You can create curves, and I can show you more. I can show you more details of this that show that if you want a response time, let's call this performance. So this would be the response time would decrease, so performance goes up. It's going to look like this, right? If this is cost, right? The more there's at some point in time to get a delta performance, you really got to spend a lot of money, right? Some of it can come with software optimizations, slightly faster CPU, faster access time to disk, but at some point it gets really expensive. And so this is where you don't want to find yourself in this area where you may get shut out of the business because your cost is too high. Instead, what would you rather do? If you were a requirements engineer, if you were bidding on this, this is where you may want to go back and say, hey, you know what, Mr. Customer? Okay, if you don't want to spend all that money, if you just relax that a little bit, I can save you a lot of money. Let's work on this. Should I give you a couple options and we can discuss it? That's a viable business strategy. We do that all the time. For many of these requirements, it is truly a cost-benefit type of a kind of bathtub curve. So anyway, all capacity requirements, you're going to experience that kind of curve because CPU, memory, I/O, that gets expensive. You want to be able to manage that and not blindly go bid on or try to maximize one of those requirements when without understanding the other costs associated with that. Okay. Now we can also say a similar thing about accuracy, but accuracy requirements, I'm just going to cover a few more categories for you here real quick. When you talk about accuracy, these requirements, it's both range and precision of data. How large, how small can data be? How accurate should they be? They're actually slightly different things. I've got an example coming up in a little bit later that'll talk about this, but you need to understand, this is another case where, again, go back to my desk camera. If what's the difference in, computing 4 bits versus 8 bits? You might say, oh, what's the big difference from a precision or accuracy perspective? We'll just use the larger. Okay. Well, if you overcalculate all the time, this actually will have an overall increase in power in your system by overcomputing. That's just one example. It may also take more time depending on the type of computing system you're using. If you get up into 32 and 64-bit. So it's actually pretty important to think about what's the minimum accuracy and precision of your results before you start deciding on the solution. At least ask those questions. Otherwise, you may end up, again, over or under computing on some of the algorithms, and you could be wasting resource. So again, just look for, at least ask the questions. Capacity, same thing. Just going to throw these out. Capacity, I got a couple sample requirements. I'm not going to read through all of them. They're there for you to read, but keep in mind whether you're doing your project or in your homework, sometimes these are subtle. People don't always think of these, but if you're developing an application, or you're asking somebody to build an application for you, is it important for you that they only use a certain amount of memory? I can tell you that Nokia, because I worked with them for a long time, this isn't a Nokia, but Apple I'm sure has the same thing. They're very, very interested in how much memory an application would take when it's compiled onto their phone, because the more they can fit on, the better. More differentiating it was if they can have more stuff on their phone. So what did it drive? It actually drove a requirement into my team directly, to have our compiler optimized for code size. Because the more they can squish it down in code size, the more they can actually fit on their phone. So it was a very strong requirement for, so as a matter of fact, I would have, it was a challenge I had, competing requirements I had. When I was managing a compiler team, I'd have one set of customers, my cell phone customers were very interested in code size. And I had another set of customers like automotive and networking and such that were interested in performance. Well, as you probably know, you can't get both. If you compile for performance, you usually end up getting more memory and vice versa. So we had to put these two, we had these options in the compiler that would allow someone to switch either one on and off. And then you had to optimize for both. But that was an ongoing requirement that I had for many years for these different customers that support both of these. So that's just an example of how those things would flow back into a product development team based on the type of product that we were building for. Accuracy, same thing. If you're, we're going to talk about problem framing here shortly. Anytime you're getting any data from the environment, okay, it's generally going to look like this. So this is an example of where accuracy comes into play. Almost everything, if you have a software system, and this is the environment, that environment is analog, right? Anytime you want to sense or get anything from the environment, what do you normally have to do? You have to put a sensor out there, and then you have to put some kind of an A to D converter before it can come into your system. Well, how do you, what happens in this area here? You have to convert this into what? Some kind of digital representation. And a data converter can be of various accuracies, right? You can have a 2-bit data converter or A to D converter, a 4-bit, all the way up to 16 and beyond, right? What happens when you add more and more bits to your converter? You get more accuracy, right? But it's also more expensive. So if you're building this, right, you have to at least ask the questions. If someone out here says, hey, you know what? I want you to detect sound pressure, voice, okay? Because I want to take that voice and do something with it. You have to understand what's the accuracy of that voice. It'll have a big impact on what you want, fidelity, right? So, make sense? So you have to be able to ask those questions. So all these again are falling under this non-functional requirements category, but they're all important. And some of these are important based on the system. Okay, we talked about performance already. Skip that. This is just again a few examples of how you might specify performance requirements. The only thing I'll say here is be careful on don't build yourself or box yourself in. Like here, some product can support 200 payment transactions per second during peak load. Okay, so during peak load, I can go up to 200. It's okay if I don't exceed that, but Okay, CPU usage, less than 75%. I used to get this one all the time in defense. I can't exceed 75% CPU utilization. Why is that? Because sometimes your customer wants to use the 25% for other stuff that they want to do, okay? Or for growth and expansion. And then this, a simple report shall take less than 215 seconds for most of the use cases. Why not 100%? Because you might have that one that's just going to really stress the system, and you don't want to have to deal with that, right? Another example is cell phone base stations. If you've ever been in a situation where sometimes if you've been to a ballpark when there's a lot of people in one concentrated area and you're trying to make phone calls, sometimes your calls don't go through. So what's happening there is the base stations. So of course, these things are getting better and better, but base stations are not designed to handle infinite calls per second, right? They're designed to handle some average number of calls per second. Anytime there's a crisis situation in the city or in the world, this happened, I think, in Boston when they had that bombing. Everyone was trying to call in. All the calls weren't getting through. These systems are not designed to handle infinite scalability. So they're designed to handle average and peak, but they're specified. Peak load of, average load of, those have to go into the requirements as well. So it's okay to say, you don't have to support every possible condition, like when there's a crisis or emergency. That's just be clear about that. There's some psychological limits also. Now, some of these are applied to user interface design. These have to do with things like if you are going to perform a task on the computer through with a user interfacing to the computer, that's going to take, for example, more than 20 seconds. There are certain things you have to do to let them know that you're doing something. Can you imagine if you type something in and hit return and nothing happened? Give the user feedback. Hey, listen, I'm off doing this. In the old days with modems, you'd hear all the fancy noises and beeps and this and that to let them know that they were connecting, because anytime you're connecting through hardware in a computer going external, normally your software can't really do much of anything else. So the way they would tell you, hey, hang on, would be all these fancy beeps and stuff. Even today, downloading large files and such, you have to let the user know. So so there's a whole set. I should have put a table in here. There's kind of a default table I teach in my user interface class. Anything over 2 seconds, do this. Anything over 10 seconds, do this. Anything over 20 seconds, do this. Mainly, it's just informing the user that, for example, anything over that's going to take more than 10 seconds. Use the cursor. Just put the hourglass and spin it. Just let them know something's happening. If it's a really large file over 10 to 20 seconds, put the progress bar, right? Anything more than 20 seconds, maybe give them some other freedom to do something else. So there's some rules that go along with user interface design. Again, don't insist on stated response time in every situation. That can really, if you're held accountable to that, it can be very expensive to get that optimized properly. Okay. Worst case, extremely rare, so don't worry about always meeting that. You can say, you know what, there's some cases where I'm not going to meet it, whether it's 95%, 90%. There's different curves you can apply to that. There is some modeling. Do I have my modeling system? Yeah. There is some modeling you can apply to this for probabilities of 95%, 90%, 85%. Of course, the cost gets lower as you relax that limit. Modeling can be used to help you specify which curve you want to fall on. And then multi-user, you don't want to, if you're designing a distributed system where you've got the network involved and someone says, we expect you to meet a certain response time and you have to go over the network, to get something done. Obviously, you don't want to be impacted by something you can't control, like delays in the internet. And so normally you would not agree to this, to do this type of thing. If someone asks you to do this, be very cautious. What you can do is bid on it, bid the response time as if the internet had zero delay, and measure everything else but the network, and then add the network in, or have your customer take responsibility for the network delay. See what I mean? So you compute how long it takes to do all your calculations, all your rendering, up until it goes onto the network, and then the same thing on the response side, and you don't have to worry about the network traffic, because that's not really your area of responsibility. They could ask you to do that, but you normally would not sign up for that. Your customer should go more towards an independent service provider support for any internet delays and add that to your response time, but you should not take responsibility for all that. Okay, now usability. I'll talk more about usability, but you actually can measure usability. Usability is fit for use. Now, what does fit for use mean? It means all the tasks that your user expects to be able to do, you've got covered, which generally translates into the functional requirements. So fit for use, so in other words, if my application should be able to do a print. Yep, I can do a print. You know, you want all the functional stuff is there, plus this more vague term called ease of use, ease of learning, efficiency, things like this. This is much more subjective, but also has to be quantifiable. Those are the usability factors. So usability, again, is tasks plus usability factors, and it has to be verifiable. So if somebody comes to you and says, a new user should be able to do this, you should define what new user means. You know, less than X number of hours or years or what have you on the system. An experienced user, same thing. We can develop systems to get high usability. I'm not sure if I've had this discussion with you yet. We've talked about other forms of non-functional requirements, but how do you get high usability? How do you get ease of learning? What does that mean? How do you get ease of remembering in a user interface? What are some requirements that would drive ease of, pick one of them, ease of, let's take task efficiency. How would you quantify that, task efficiency? Well, you can say something like, you know, you should be able to reserve this conference room using this conference reservation system in less than 10 seconds. That's measurable, right? What if you don't want to use clock time? You can say, well, I should be able to reserve this conference room in less than 6 commands or clicks. Or I should be able to reserve this conference room with less than one error, meaning you performed an error trying to reserve the conference room. What's ease of learning? What does that mean? How would you actually form requirements for ease of learning something? Well, ease of learning could mean that, you know, throughout the application, Control-C means the same thing everywhere, for example, okay? You know, and all the other control functions, you know, they mean the same thing no matter where you are. That's one. Can you imagine if you had to learn a different combination, you know, in different modes of your application? Things like that. What's Control-C mean to you normally? Copy? So what if it meant delete? What if you built your own application and you decide, I'm going to make it delete? What do we think that would do to your users? Probably be hard to remember that, right? You know, for them to remember that. So consistency is a big thing. Consistency is a really big thing for ease of learning. Having something in the same place in the same time always. The mental model. What is a mental model? Has anybody had my user interface class? Okay. What's a mental model? A mental model is how you think something should work, right? So based on your experiences, based on your knowledge, it's how, when I press this button, here's how I expect the system to work, right? If it doesn't work that way, you're surprised, right? So if the application you're building matches the user's mental model, so it works the way they expect it to work, that's an ease of learning. So all these things fall under, you know, usability. I can go on and on, but those are just a few examples. But very, very important that we have these well specified early on. Okay. Here's a few usability requirements. I'll just let you read through them at your leisure. But you can see, you know, most of these also, again, have quantifiable requirements. We're going to develop prototypes in this class. And with a prototype, you can actually say something like this. The system shall use screen pictures in application A or as shown in this prototype. And you can, because it's very difficult to specify a user interface look and feel. So you can actually develop a prototype and put it in your requirements document and say you want it to look like this. So we're gonna do that for our projects as well. Okay, now how do you test usability? Just a couple more words on this. Some of the more effective but also simple approaches. One is called observe. You actually watch someone use the system, and you sometimes you can videotape them, and you can see by looking at them where they're struggling. Okay. Thinking out loud. Has anybody heard of this approach? So thinking out loud is where the person that's using your prototype or system, they're like this using it, and they're saying, okay, I want to try to insert a slide. So I'm going to go up here. I see this insert thing. I'm going to click on that. Okay, I can't find any place to insert a slide, so I don't know what to do, huh? Okay, maybe let's try doing this. Oh, okay, now I can insert, you know, see how I'm talking through it? So with the thinking out loud, that's really what they do. They actually talk through everything that they're doing, and they are recorded, and you can learn about how they're thinking through the problem and where they may be getting stuck, and that can also help you refine that and generate better requirements. And heuristic evaluation is a 10-step approach of looking for different things in the prototype. We'll talk more about this when we talk about prototyping. I'll skip that for now. Real quick on security, big growing area of requirements, concern. I want to talk a little bit about this. Threats from security, and we're going to talk about misuse cases too, I think, probably next class. We'll touch on that a little bit. But threats come from really three main areas. Someone looking at stuff coming into your system that you're building, someone being able to look at or something happening with where you're storing data in your system, and then someone looking at stuff going out of your system. Three basic areas, and you should really consider what potential security requirements you need to have at each one of these kind of transition phases. It's hard to specify. Sometimes these are referred to as a shall not requirement. How would you specify a requirement that says I shouldn't be able to, you know, hack into my cell phone? I mean, how do you actually word it? Do you say the requirement should be no one shall be able to hack into my cell phone? If you put that, literally, if that was a requirement, no one shall ever be able to hack in, do you think anybody would sign up for that requirement? No, of course not, because there's always someone eventually will find a way of doing it, right? There's always some way, with some time and some technology, of eventually breaking in. So you never want to sign up for a requirement like that. Instead, you might say, you know, no, it shall not be possible to break into the system within 10 minutes using these technologies. At least then you can bound it, right? So sometimes these are called a shall not requirement. They shall not be able to do something. It's very hard to specify a shall not requirement. It's even harder to test it. How do you test a shall not requirement on security? What do you do? So someone gives you that requirement. Shall not be able to, you know, sabotage or otherwise break into my XX system. How do you test it? So certainly part of it can be looking, well, part of the approach of validating those requirements are looking, you know, looking at doing reviews, looking at the design, looking at the data going in. All those checks are yeah, that's definitely one way. But then again, when testing it to make sure that it's actually working, you might want to get a hacker to actually try breaking into your system, right? which is actually how they do this a lot. I had one of my colleagues that's in Dallas here, he works for Raytheon. He was given the job while he was waiting on his clearance. They have networks, big computer networks on these ships now, very, very advanced computer networks, and they're concerned about security. So while he was waiting on his job, what he was asked to do was, I thought this was a really fun job. He thought it was boring. I thought it was a really fun job. All he was asked to do was try to find ways of breaking into the system. That's all he had to do all day long. And if he found a way to break into the system, he had to document that approach, what he did, and then they would go off and they'd fix it, okay? But that's what his job was try to hack into the system. Well, that's actually how you do a lot of security requirements validation or testing, is you actually literally put a guy down there and they try to break in. And some of it can be done by mathematics and analyzing the algorithms, but some of it's done by, in the real world, actually getting it out there and letting someone try to hack in. And so that is actually a valid approach. There's a lot of things that could occur if there is a breach. Accesses, even you have to look out for things like disk crashes. That's why you have sometimes redundant disks. Same with computer crashes. That's why you may want to have a requirement, if you're building an IT application, to have a requirement for backup occasionally to get around that, because that is a security risk, right? You lose all your data, that's a security risk. And then, of course, sabotage, fraud, and viruses. Every one of these has a set of requirements that needs to be considered to either detect or prevent. Sometimes you can't prevent everything, so you have to be able to detect. A denial of service attack is hard to prevent, but it's relatively easy to detect and then work around. So these have to be considered. So here's kind of my roll-up, threats and possible requirements. So this is, again, for your reference, but basically threats on input. It could just be, hey, you know what, I entered the wrong data. But that could be a security issue, right? Right? If you enter the wrong data, that could possibly be a security issue. Let's say they accidentally typed in a password when they thought it was literally a password they were typing in as input data. So they can make a mistake or illegal access. All these are input. It violates, if you're familiar with security, violates different aspects of security. This one, usually input threats violate integrity, authenticity, and confidentiality. And there's some requirements around it, like logical checking, having signatures, digital signatures, and encryption. Again, I'm just giving you things to think about. These are areas where you have to go look at more deeply what kinds of encryption, what kinds of signatures. I'm not going to talk about those specifics because it varies by application. But these are the areas you have to go start asking questions about to your customer. Storing information, such as crashes or errors or viruses. Again, it violates availability, integrity. Normally, redundant arrays of independent disks or RAIDs help. Different test techniques and even firewalls, these could be requirements you add into your system. And then on the output side, or anything transmission, fraudulent data, viruses, violates, again, availability and confidentiality on the output side, because people can read your data now. So having multiple lines, potentially auditing, encryption, these all help for that class of threat. Yeah.
Can you elaborate the multiple lines? How they are having the...
So multiple lines, if you send, depending on how you're outputting data, sometimes redundant lines. Okay, so you're sending the data over multiple lines to the same destination and checking at the destination. It's one class of output threat. Okay, when you're okay, so here's my software system. So I have stuff coming in. So here's my someone could be kind of looking at data coming in. I've got storage related issues, and then I've got data going out. Now where data goes out, you can have a person looking at the data on the line, or you could have someone picking the data off before it even goes out and doing something with it. Like, for example, let's say you send an email. Someone could take that email, go over here, do something with it, then put it back out on the line. A classic example of this is you may send an output, sell 100 shares of some stock. And then some fraudulent guy intercepts that message and changes this to 10,000 shares. Actually, buy would be even worse. Okay, and that goes to the broker. Who's liable for that? The guy who made the order. Unless it's very difficult to win over on some of that, unless you can prove that. Anyway, the point I'm trying to make is, if you're trying to look for something going to the destination and preventing this type of thing, sometimes multiple lines can help that. Okay, so different techniques based on what you're trying to prevent. Okay, make sense? Okay, so again, categories: input, storage, output, violates different aspects of privacy. Different requirements can be used to solve these problems. Okay, again, we'll touch on certain examples of this as we go, but there's a lot of different types of requirements, like for example, encryption, firewalls, et cetera. It really all depends on the kind of application that you're building. Okay, but those are the categories. So safeguards, again: prevention, detection, repair. I can prevent certain errors. Denial of service, it's more about detection. And then in all cases, it's how quickly can you repair, get back to normal. Like a backup, easy to repair. Denial of service, easy to repair. Crash disk, potentially. It all depends on again, the class of security. Here's, again, just a couple other areas of potential compromise to be aware of. I just talked about physical distortion, but look at all these other ones. This is actually why security is becoming a really big area for many applications. One of the biggest areas right now, right here, cell phones. You probably heard a lot. These always make the news, right? The most recent one was what? Last week? What was the recent? I mean, it seems like every week there's one. The iCloud. So Apple had to put out a few patches to that. It's a really big area. So when you're thinking about requirements, always think about what are the security requirements I need to consider. I always like to look at this list. What are the biggest potential problems with application XYZ? Like with a cell phone, which of these do you think might be most important with a cell phone? Maybe illegal access, a little bit about stealing passwords, not so much wiretapping, right? So some of these apply more than others. So you just got to think about which ones are most important to you. Okay, let me transition to this other area. So what I did, what I just finished there is I wrapped up a set of non-functional requirements for discussion on that topic. What can we say about non-functional requirements? Right. First of all, there's a lot of them. What else can we say? They're harder than functional requirements because you have to get quantity. It's easy to be ambiguous. It has to be fast. It has to be usable. So easy to be ambiguous. Think about all of them having some quantitative, part of it. Therefore, you can test it and measure it. There are exceptions. I talked about open metric and open target, where you truly want to have some flexibility in what you sign up for, because what? Because you can end up with a really high cost if you have to go all the way and implement. So you want to sometimes get help from your customer on what they would prefer, what they think, what they like. Make some recommendations. So there is always exceptions to that rule. And then just, again, look at the non-functional requirements that make sense to your project. Not all of them will apply. Some cases they won't. Performance in some cases isn't a big deal. In some cases it is. You just have to go down that whole kind of taxonomy that I showed you earlier of non-functional requirements and kind of check off the ones that make sense and then drive them into the right amount of detail so that you can actually go off and verify that you've actually implemented those. Okay, so that's kind of the quick summary on that. But in a very important area, what I find to be one of the most troubling areas of requirements engineering is dealing with the non-functional requirements. That's why I like to spend some time on that. Okay, I want to move on to another kind of section or topic. We're going to get into an area that's also kind of interesting. People tend to skip this whole thought process when they're thinking about systems, and I want to touch on this a little bit and show you a way of thinking about the problem that oftentimes is forgotten, but can lead you to discovering new requirements that can really benefit the project success, and it'll allow you to find these things a little bit earlier rather than when it's too late. So we're going to start off by talking about domains. Now, oftentimes when you think about a problem we're trying to solve, and we've already had the whole discussion on defining the problem and all that, you need to look at the key domains of interest in solving the problem. This little Venn diagram shows a classic view of some key domains. It shows, let's start on the right-hand side, the machine domain. That should be the easy one. What's the machine domain? Think of that as a computer that your application is going to run on, right? And if someone was describing your application running on a computer, they would be, it would be in terms of computer programs, data structures, operating systems, things like this, right? That's the implementation of whatever you're going to build to solve the problem, okay? Now, let's look on the left-hand side, application domain. What does that mean? So the application domain sometimes it's referred to as the domain of interest. This is where, when you write your requirements document, you write it from the perspective of the application domain, not from the computer domain. So for example, let's say you want to write a requirement about, let's say you're building a trucking system. This is a nice, interesting one. So you get asked to build a trucking scheduling system. Okay, now here's the deal. You guys have all seen those 18-wheeler trucks, right? I see them every single time I drive up here on 35. Okay? These trucks, 35 goes from Canada to Mexico, and almost all the traffic and all the trucking seems to go right up and down that spine. There's thousands of these trucks on I-35. So they're carrying all types of cargo. One of the big things about a trucking company, what do you think one of the biggest expenses is in a trucking company? It's the gas, right? And so if I can optimize, if this truck has to make 25 stops in a week of traveling to drop off all this cargo, if I can optimize the route that truck takes to pick up and drop off cargo, I can save on gas and improve my profits, right? And you multiply this by 100 trucks or 200 trucks or 1,000 trucks, I'd definitely be willing to invest the money to build a system that can optimally schedule my truck traffic all across the United States, okay? The other thing is, in some cases, these trucking companies can get into a really big problem with weather. So let's say a truck is driving down through New Orleans, and we detect that this other hurricane in the Gulf is going right towards New Orleans. Well, if it gets stuck in a hurricane, I'm just making this up, they could be literally off the road for 2 or 3 days. And what's happening when you're not on the road driving? You're losing money, right? A lot of these trucking companies get paid by, how quickly they can drop their cargo off at different locations, right? So if I can design a system that can route these trucks around bad weather and other inclement weather, construction, things like that, I can probably save some money, right? So this software system is going to be built to communicate to these trucks the optimal route that they should take to make their deliveries. And it'll be dynamic because as they're halfway through their journey, they may get a new place to go pick up something or whatever. Okay, so now when I'm describing the requirements for this trucking system, like the trucking scheduling system shall be able to route around bad weather. It shall be able to take the optimal route from destination A to destination B. And I'm describing the trucking scheduling system. Am I describing that in terms of data structures and operating systems and things, or am I describing in terms of like what's happening in the real world? It's the latter, right? Okay, so that, if I were to draw this, so that's the Venn diagram I was trying to refer to. So we have a machine domain, and this is data structures and operating systems and all the implementation of the software. But really, from a requirements perspective, we're talking about, this is the application domain. We're really, this is where the requirements, that's the requirements, this is the software. And what we're talking about, we're using terms like trucks and routes and weather. Now we're talking about real world stuff, right? Real things. Data structures, operating systems, etc. Okay, this is the software. Okay, now what's this thing right here? What's that overlap? Sometimes that's referred to as the specification. Another way to think about it as the interface. So if, now try to visualize what's going on here. Let's say I build this trucking scheduling software. And where would that software reside? It might reside in the home office of the trucking company. I'm kind of just making up in it. So it's going to reside on someone's laptop, and there's going to be maybe a person sitting at that desk, and it's going to be looking at this program, running these different scheduling algorithms, and then that person is going to probably be somehow communicating that information to real trucks on real roads, right, in the US. And it can do that, maybe it's an email, maybe it's a text message, maybe it's some kind of GPS thing, but that interface between the machine, the laptop running all the software, and the real world might be this person operating the system. Does that make sense? Can you see how that might work? That actually, you know, it could be UPS. I could have used UPS as an example, but that's kind of how it works. So if you go back to the screen I was trying to draw here, so now hopefully this will make more sense. On the right, the machine domain is the computer sitting in the office. On the left-hand side are real trucks driving on real roads. That's how we're going to describe our requirements. And then in the middle is kind of the bridge between the machine and the application domain. Sometimes it's the interface, specification, and that could or could not involve a person. So in other words, a real user interface, right? If it does involve a real person, then this part right here would involve user interface design, which is going to be a set of requirements, and we'll do that with a prototype, which is what we're going to do in this class. We'll design a prototype for this, okay? Now, some of these, I know this is getting a little bit abstract, but bear with me because we have to have this discussion to really understand how to frame the problem. We've discussed the problem, but now we're going to frame it a little bit differently. Now, out here we talk about things like domain properties, D. These are things in the application domain, the real world, that are true whether or not we ever build the system. Give me an example of that. Well, an example of a domain property, I'll give you a simple one. The sun's always going to come up in the east and set in the west, right? Highway 35 is always going to go north and south. That's always going to exist. It's never going to suddenly go east and west, okay? Those are these are things that are always true. The temperature cannot fall more than 1 degree per second, things like this. Things that are applicable in the domain that you're trying to describe. You can even, another example might be coverage. Let's say this particular application, this trucking application, somehow you're going to communicate with text messages. It might be a domain property that you specify. Here is the LTE coverage data that exists in this. You know, that could be a domain property too, okay, if it's important. And then we have requirements. Now these are the things that we're ultimately going to write. Okay, the requirements, these are the things that we wish to be made true by delivering the proposed system. So in other words, if one of the things I wish to be made true is that I can direct trucks to take certain routes to get to their destination, I would specify that by writing the requirements for that, right? Okay. And then the specification description of the behaviors that the program must have to meet the requirements. And so normally that could be programmed or done through a user interface. Like, for example, a person could be calculating a route and then giving that to the driver. That's done through this interface. Okay? So far, so good? New concept, so I want to make sure I understand it, right? Do you think this computer can ever make a truck turn left or right? Yeah. By calculating a route and sending it to the trucker, and then with the assumption that the trucker is going to listen and turn left or right, yeah, this computer can actually have causal effects on the real world, right? Okay, let's go on. All right, now, when you're developing software, which is this black box in the middle, anytime you're trying to understand the environment, I drew this picture quickly for you earlier, anytime you're trying to understand how your software system will interact with the environment, you have to understand what's sometimes referred to as a 4-variable model. You have to understand how you're going to get data in, how you're going to get data out. And I'm going to refer to this several times, probably in the next several lectures, defining the boundary and what's coming in, what's going out, the ins and the outs. Well, when you have an environment in the picture, like, for example, a truck in the environment, okay, you have to understand 4 key things. Okay, the first thing is, first of all, you have to understand the environment well enough to understand what it is that I need to monitor. Okay, maybe I need to monitor truck speed, truck location. Maybe I need to monitor temperature, just throwing out a couple things. Whatever those things are, you need to identify what those monitored variables are. Now, let's say I have to monitor temperature because depending on whether temperature is too low or too high, I may route these trucks in a different direction, okay? Well, I have to understand also how I'm going to get that monitored variable in the real world converted to input data. This input device is that sensor I drew earlier with that A to D converter. That's what that would be, right? Some device that gets this monitored variable into the software. And then on the output side, when I take a digital output, like it might say go to this location in digital form, I have to have a way of converting that to some controlled variable on the output side. So a controlled variable might be speed. For example, I'm throwing out different examples for you. Let's say you're monitoring the motor on a refrigerator so that you can keep the refrigerator cool. You may, depending on certain conditions, want to control what? Control the motor speed. So you would control the RPMs of a motor by sending a signal out, depending on some requirement that temperature can't go above or below a certain range. There's all kinds of examples of these controlled variables, but basically what it is understanding from the environment what you have to monitor and measure and what you have to control, and then how to get it in and out. Now, when you're writing a specification of software, you would be concerned with that. The actual input data, the output data. If you're just concerned about the software system, if you're really looking at more of a systems perspective, so not just that software component in the black box, but more of the whole system, then you may look at the whole environment. So this is where you would consider some of the domain properties as well as the requirements. Some of the domain properties, I've got some examples coming up, are going to constrain how the environment can and should behave. For example, you heard me mention temperature will not drop more than 1 degree per second, which I think is a real domain property. I think that's true. And there may be others as well. Okay? So again, depending on your perspective, you might be writing a specification for a software component or for a full system. For a full system, you have to understand more about the domain. And I'll show you why. I'll show you why that's important. This is a more generic representation of that. Again, it's called the 4-variable model. This is the software I'm building, the software to be. This is the environment. I need to monitor variables. Usually I monitor the variables with sensors, and I convert those into input data. I have to sometimes control devices. Sometimes those are referred to as actuators, like a motor for a refrigerator is it's an example of an actuator. That's a generic term. And that might control the environment. So for example, let's say I wanted to monitor the speed of a train. okay? From the environment, I'd have to find a way of getting a variable, I'm calling it train speed, via some sensor, okay, some sensor, and converting that into input data, which I might call measured speed, which might be a digital representation of the train speed, and then do something with it, and then maybe I want to control that train speed based on what I'm reading back out to the environment. So there's the four key things here are sensors and actuators. Those are just different terms of saying input and output devices. The software I'm building, and then the environment I'm interacting with. Okay. Now, if you're a system engineer, okay, I teach a systems engineering class as well. If you're a systems engineer, you're going to be looking at this from a systems perspective. So you're going to be looking at monitored and controlled variables. If you're a software engineer, only you're going to be looking at input and output data. So you're going to be more focused on this, okay? I bring that up because depending on your role in industry, it may be more systems, it may be more software. As an embedded I'm more of the embedded space where I'm interacting with hardware a lot. My software interacts with hardware a lot. I'm more on the systems perspective. I have to understand more about the environment, so it's more monitored and controlled variables. But it will vary based on at what level you're trying to operate at, okay? So that's called the four variable model. Now, when you're, you never thought requirements would be so difficult, but it's really not. I'm just trying to add a few more complicating factors to make you think about this. To get a system requirement right, again, so what's a system requirement? I'm looking at this whole thing from the environment perspective. If you go back to this page, it's this whole thing, okay? If you're looking at it from a systems perspective, a system requirement requires the following. It's not good enough to say, to implement the software requirement only. In other words, it's not good enough to say, if you want to look at this thing from a system perspective, it's not good enough to specify just the ins and outs. You also have to do the following. You also have to be able to specify the key assumptions that are satisfied by the environment. In other words, you assume the environment's going to act a certain way, right? And you have to understand the key domain properties that exist in the environment. You know, roads go north and south, temperature, you know. All that has to be specified properly in order to really understand the system level requirement. Let me give you a couple examples of what happens when you don't think about all these, okay? It'll make this be a little bit more clear to you. I've got three examples. This first one happened, you know, a number of years ago. This Lufthansa Airbus 320 was landing in Warsaw. You can read the whole story out here. Okay, basically, what happened was, this plane ran off the runway, and in a thunderstorm, it ran off the runway and it killed a bunch of people. Okay, now when they looked at what happened, this plane was coming in for landing, and the red means wheels off the ground, green means wheels on the ground. The plane was coming in for a landing in a thunderstorm. It came in farther down the runway than it probably should have. I think that was when that 770 meters mark is when they were expecting the green. So it came in late or long. It didn't get both wheels down because it was a little bit cockeyed, so it got one down, and the other one came down a little bit later. So by the time both came down, it was quite a ways down the runway. It still could have stopped in time, but it didn't. And it didn't, when they looked at why it didn't, why it slid off the end of the runway, even this condition should have been accommodated with the system, with the airplane system, but the system requirement was not implemented properly, and I tried to specify it here mathematically. So the way you would read this is a little bit of kind of predicate logic here, but the way you would read this is the following. The system requirement was that the reverse thrust, now the reverse thrust is just reversed engine thrust, which is one of the primary ways of stopping an aircraft when it's landing. This statement says the reverse thrust is enabled this backwards and forwards arrow means if and only if. So reverse thrust is enabled if and only if the plane is moving on the runway. You don't want to put reverse engine thrust when it's still in the air, okay? Okay, now, the engineers took that system requirement and implemented a software requirement that basically said, again, this is monitored and controlled variables. The inputs and outputs were reverse on, so reverse thrust on. So reverse on, if and only if. How do you detect moving on runway? It's a good statement to say about the environment, but how in real software do you actually detect something moving on the runway? Well, these aircraft have wheel pulses. And so what happens if you're detecting wheel pulses? What's the implication? That wheels are moving, right? Wheels are moving. The implication is it's on the ground. Okay, so turn the reverse thrust on if the wheel pulses are on, if I'm getting wheel pulses, okay? Now I also have to make some assumptions on the environment because you just heard me make two of them. I just made the assumption that if I'm getting wheel pulses, then I must be on the ground, right? So wheel pulses on, the assumption, wheel pulses on if and only if the wheels are turning. That's the assumption I'm making. Is it possible to get wheel pulses when the wheels aren't turning? I'm going to say in this specification, the assumption is no. I can only get wheel pulses if and only if the wheels are turning. Also, the reversed on if and only if the reverse thrust is enabled. So if the pilot puts reverse thrust enabled, the reverse thrust is going to go on. I'm making those assumptions. So far, so good? Now, the domain property specified for this system was moving on runway. So the plane is moving on the runway. I'm going to say that the plane is moving on the runway if and only if the wheels are turning. Make sense? So far, so good? Okay, that was a bad domain property assumption. Anybody tell me why? What happens when you're hydroplaning? Has anybody heard of this term? When you hydroplane, you are sliding down the runway with your wheels not turning. So when this aircraft landed right around here late in a thunderstorm, so wet runway, the wheel pulses weren't occurring, at least not in a predictable order, because the wheels were just sliding down the runway. Hydroplaning. So what happens if you just reverse your way back up this? If the wheel pulses on, wheels turning, so I'm only going to turn the reverse thrust on if what? Go back up here. When do I turn the reverse thrust on? Only if I'm moving on the runway. I'm moving on the runway only if the wheels are turning. If the wheels weren't turning, what happens up here? I don't turn the reverse thrust on, which is the primary braking thing. So this plane, the reverse thrusters came on way too late and it ran off the runway. Okay? So here again, example of, I implemented the software based on this 4-variable model exactly the way I would expect it to operate. However, because of not specifying properly assumptions and domain properties, the requirement, which was implemented exactly the way it was specified, was not the right one. Does that make sense? So it's very important to have all three of those understood when you're looking at requirements. Let's take another example. In England, or actually it was the UK, I'm not sure if it was England, but guy pulls up to his country estate. This is a picture, a estate out, a big house out in the country where you have a gate protecting the driveway and then this long driveway that goes up to the rich house. That's why I showed a Bentley here. I'm not sure if it was really this car or not, but it was a car, pretty big car like this. This car, what ended up happening, let me describe what happened. The guy gets out of his car. This happened long enough ago that there weren't the automatic gate openers like we have today. So the guy got out of his car, goes up to the gate, opens the gate, and during that process, the car brake disengages and the car comes forward and crushes the guy against the gate and kills him. Okay? That's what happened. So they went and looked at what happened. What happened that caused this thing to occur? Well, again, it could be, they looked at this thing from a requirements perspective. It was very interesting. These cars have a handbrake that you pull on, and then you can release it to start and stop the car. And think of it almost like an emergency brake kind of thing. The handbrake shall be released if and only if the driver wants us to start. So if you start the car, the handbrake is on. If you release it, the car is going to start going forward. Okay, that makes sense. The software and other mechanics, because there's only, at this point in time, there's only actually a very little amount of low-level software that controlled this. The handbrake control shall be off if and only if the normal running of the motor is raised. Now, what that means is the following. If a guy gets in the car, the handbrake is on, and if he presses on the gas pedal to go, it was another way of releasing the handbrake. So, and that, as opposed to him always having to reach over and disengage the handbrake, if I get in the car, put my foot on the gas, it automatically disengages, expecting that, hey, you're pressing on the pedal, you want to go. I'm not going to keep the handbrake enabled and maybe cause engine harm, so I'm just going to release it and you're going to go. Okay. So how do they detect that somebody wants to go? It's hard to detect necessarily when, well, there's a couple different ways of doing this. You can detect when somebody presses on the pedal, or in this case, you can detect when the RPMs of the engine goes up. Okay. So the assumption that was made was, well, the driver wants to start going if and only if he presses the acceleration pedal, right? And then the domain property assumed for this was the normal running of the motor is raised if and only if the acceleration pedal is pressed. In other words, you should be able to follow this logic, but you press on the pedal, the assumption is the engine RPMs goes up. That means the driver wants to go forward, handbrake disengages, I go forward, okay? Now, the use case for this, or the situation that caused this problem, was the following. I didn't give you all the information. When the guy got out of his car on a hot summer day and left the car door open, like many of us do, get out, leave the door open, go over, open the fence, get back in your car. It's a pretty common activity, right? Well, what happened? Anybody? Connect the dots? Well, that's actually what the brake was preventing, is that 5 mile an hour kind of movement. What ended up happening in this case was, the brake was on, but I gave you the hint, hot summer day. This year the car, or this brand of the car, had the air conditioning tied into the same belt as the engine. So what happens when the air conditioning kicks on? Why does the air conditioning kick on? Because he opened the door and it got hot. Air conditioning kicks on. Back in those days, it raised the RPMs of the engine because you're trying harder to drive the AC, and the brake released and went up and pinned the guy against. It didn't kill him immediately. But he was pinned against the fence in the middle of the country. Nobody driving by. He eventually died of his injuries because nobody can get to him for hours in the hot sun. Okay, but that's what happened. That's kind of the logic behind a semi-flawed requirement, at least from how the domain should operate. The domain in this case was partially driven by the environment. And then finally, went a little bit closer to the home. And has anybody ever driven the subways in Manhattan? So subways are always an experience in Manhattan. But in this particular case, back in the 90s, they replaced some of the subways. Now, if you've ever been in Manhattan and driven the subways, you know that they really needed to be overhauled for many years. And they finally got around to doing it incrementally. And they replaced these subway cars with much larger, more modern cars. But they failed to take into consideration that these larger subway cars are also heavier, and it takes them longer to stop. Well, inside a subway, underground subway, there are a bunch of lights that are indicators when there is another subway ahead of you and to slow down. And you know, that's why you have subway drivers, because they look at these lights, and if there's a traffic jam for any reason, you know, they can slow the subways down, and they're not fully automatic. And in this case, when they during one area, particular area where the subways can get up a lot of speed, there's several parts of Manhattan where you can really work up a lot of speed. These lights were all timed to reflect a stopping distance for the old cars, and when they put the new cars in, that stopping distance, because they were heavier, was longer, but they didn't update the lights accordingly, and so this particular instance, you know, one slammed into the other one. Again, this is one where, again, it's a failure to understand the entire system or domain. So when you're making requirements changes in this case, this is an area where they probably got 95% of the requirements right and missed a key aspect, and because they didn't properly understand the domain, and this incident happened. So 3 examples of what? It's not just understanding how to take a very specific translation of a system requirement into a software requirement. We have to understand the domain properties and the assumptions on that domain to really make it all work, right? All has to be there. Okay. So far we good? Okay, now I need you guys to help me with a problem. And here's the way we're going to work it. And this happens a lot. I mean, this type of approach we're going to take here. So I am a researcher at SMU. And I'm in my office at SMU. I'm at my computer. And I'm doing some research, okay, funded research. And I believe I have a very innovative way of measuring and, for once, putting an end to the debate about global warming. I'm going to actually, we've got some algorithms that can prove once and for all whether there's really global warming or not, right? Now, in order to do this, one of the key things I need for my algorithm is I need to get weather information from all different parts of the world, okay? And I've also got some constraints. Since I'm a researcher at SMU, I have limited money, okay? I'm a graduate student, limited money to spend. And I've also got some non-functional requirements that I need to meet. We just got through talking about non-functional requirements. I got some non-functional requirements in order to make these algorithms work that deal with things like accuracy. I need a certain accuracy. I need a certain timeliness of the data, like, you know, getting into my system to do all these computations. We talked about all these already, right? So this shouldn't be new to you. Okay, now, but the thing that's really, and the global warming algorithms are that could be more of the functional requirements. Now, the challenge I'm having is I need to get access to weather from all over the world. And I need to get it into my system so I can do this. Now, what are some ways by which I can get weather information, temperature and location, into my computer? You know, so I come to you as students and I say, help me out. Let's brainstorm. What are some ways that I can get weather information into my computer? Anybody? Weather application? Kind of like an online weather application or something like that? Okay, so I've got a lot of weather apps on my cell phone. I could, so I can do that. Okay, weather apps. Anything else? Or plug-in, okay. What else? Anything can go here. Satellite. weather sensors. I can just have a bunch of graduate students or undergraduate students. I just have you spend all day just calling weathermen all over the world, and just, you know, every hour, okay, what's the weather now? What's the weather now? I can do that. Okay. Anything else that pops out? Okay. So there's different ways of getting information into my system. Now, because I've got a set of, let's start with constraints. Because I've got certain constraints and requirements, I may have to throw out some of these ideas. So for example, if my funding is no more than, I'll say, $20,000, I think I can meet my accuracy and timeliness requirements if I use the satellite infrastructure out there, but it's way too expensive, so I'm going to eliminate that. Calling the weathermen, I can definitely fund my graduate students to do that, but you know, the accuracy and the timeliness, they don't pick up their phone, and they say it's 82 degrees out when I'm really looking for 82.13. So these guys are out. Okay. The weather apps and the plugins, the software applications, is okay, but again, I can pay for the applications, but they're not giving me the right accuracy, so I'm going to scratch those out. But I did determine that there's ways I can leverage and use existing weather sensors that are already placed in strategic locations by the different governments, and they're going to let me actually get access to those weather sensors. And so up here, I'm going to draw an example of a little house that's, I'm going to call this a weather station. Now, ultimately, what am I ultimately trying to get access to? Ultimately, I'm trying to get access to what? Weather. There's the sun. I'm ultimately trying to get access to weather, right? Now, if I had all the time and money and everything in the world, ideally, what would I like to do? If I'm a researcher, I would like to have, you know, direct access to that domain of interest, the weather, right? But I don't. I don't have that luxury because I have all these constraints and all these other non-functional requirements. So I've had to go through another approach, which is looking at other approaches of different effectiveness, and I've chosen weather sensors. So now I'm going to tap into these weather stations. Now by doing this, the guys in the back, keep a little bit just for the remote students. So I've got to tap into these weather stations. So it's not ideal, but it's the best I have available given these constraints, so I'm going to have to go with this approach, right? Okay, fine. Let's say I do this. Now I have to look into the details of this because, again, how do I get weather information? Let's say I'm going to draw a little thermometer out here. I guess I should have done this in red. Here's my little thermometer that measures temperature, mercury, okay? That's my what? That's going to be, if you go back to that 4-variable model, that's going to be called the what? If you go back to this picture here, I'll just show it to you for quick reference. If I go back to this picture, that thermometer is where on this model, in this picture? The environment. So it's one of these monitored variables, right? So, so this is a monitored variable. And what do I need to do? That analog measurement is going to come into this weather station. Well, I figured out by looking at this in a little bit more detail that that is indeed going to go into a analog to digital converter, okay? And upon looking a little bit more closely, I know that this has 3 lines of input, which basically means the output is in x.xx format. Okay, so 3 bits of accuracy you can generally get. Okay, so which is actually great because my accuracy requirement is actually I need to get to the hundredths. So this actually is perfect. Okay, good, check that box, okay? Now, I can convert it to digital, now what? Well, luckily, I can take this digital data, there's a serial input channel in that weather station, and by getting that into a serial output, I can go easily onto the network. And once I get onto the network, then it's pretty easy to get it into my system, okay? All right, now, my timeliness requirement is not that bad. It's about 10, 15 seconds I need to get this information. So I think that this network going over the internet from wherever I am in the world, I can meet that timeliness requirement. I still have to check it, but it looks like I can meet that, and it's going to be cheap enough. So all these alternatives, I've eliminated some based on my constraints. I've eliminated some based on my non-functional requirements that are important to me as well. And I've kind of worked up this way. Again, I would love to be able to have a direct access to weather, like literally stick my thermometer out of the window, but I can't do that. So I'm going to go through these weather stations, and I'm going to go through this network. Now, if you go back to, if you go back to some of these pictures I was showing you earlier about, like this one right here, machine domain, application domain. Remember those two terms? So machine domain, application domain, which, in this picture, where is the machine domain? Right here? Yeah, so that's M. Where's the application domain? It's the sun, right? That's the kind of the real world. That's how we're going to describe most of the requirements from, right? Okay, now, you're right. Machine, application domain, real world. Okay, now, what is this stuff? I mean, again, notice how that picture, ideally, I would like to almost have a direct connection to that. But in this particular case, because of various constraints and cost reasons and everything else, I had to take a kind of a different approach to this, right? And that's exactly what I did. Well, when you take this approach, these things I'm going through, there's a term we use to describe these. These things right here are referred to as connection domains. So this is a connection domain, and this is a connection domain. Now, why do we call them connection domains? Because they help connect the machine domain to the application domain, okay? And why is that important? Well, it's actually, from a requirements perspective, it's actually really, really important. Because when you take an approach like this, you essentially do the following. Here's what happens. First of all, it sets an upper boundary on how well you can fulfill the requirements. I'll give you an example. Because I set up here, this temperature is going through this 3-bit A to D converter. From an accuracy perspective, what's the best I can possibly do if I follow this path? Is that, right? That's the best I could possibly do. So if my accuracy requirement was for another bit of accuracy, I couldn't use this approach, right? So it sets an upper bound on the requirements. If I'm going over this network, I have, I can model the amount of time it's going to take to go over a network. My timeliness requirement is going to be limited by how fast I can go through that network. So it sets an upper bound. I can't do any better, okay? I can't do 5 microsecond timeliness through a network. It's impossible. The best I can do is whatever this can give me, okay? Now specifically, every time you have a connection domain, and there's 2 of them here, there's this weather station and there's network. And this is the important part you need to remember for the homework too. It always inserts, it injects 2 things into your requirement, okay? The first one it inserts is, I'll use the generic terms, is this concept of distortion. I'll just write them down. And the second one is delay. So every connection domain will add distortion and delay into your requirements. So what does that mean? So here's what that means. Start with distortion. Distortion, think of distortion as accuracy, right? What's the distortion here? I'm taking something with infinite potential values and distorting it down to something that can only have 3 bits of accuracy. That's an example of distortion. How about delay? Does it take time to go from this through this analog to digital converter to produce a digital output? Yeah, it takes a very small amount of time, but nevertheless, it takes some time, right? Okay, how about the network? The network, when I put data on a network, is it possible to get distortion? Meaning, is it possible for this data to somehow get lost, corrupted? Yeah. I mean, even if you do a TCP transmission, which is supposed to be quality, you can turn it off. A lot of people turn it off, and essentially UDP. I mean, there's multiple ways that data can be distorted, lost, changed, whatever. And then is there a delay going over the network? Absolutely. Much more noticeable than through a analog to digital converter. So every connection domain is going to always set an upper bound on how well you can do by adding 2 things into the requirement, distortion and delay. And you have to understand what that is to understand whether you can meet your requirement. So another way of saying this is, in many systems that you will be writing requirements for, you'll never be able to do the ideal case. You'll always have to use something like connection domains to be able to get, and I'll show you more examples of this, use connection domains to be able to get things in and out of your system. You have to be able to identify the connection domains. Then you have to be able to identify the distortion and delay, and then determine how well you can meet the requirements. Okay? Does that make sense? Here's another example of a very infamous, very problematic connection domain. Famous connection domain. People. Why? Because they often have to do this. That's the machine domain. That's the computer. Data entry. Anytime a user has to enter something into the system, why is that? What did I say a connection domain always inserts into the equation? Okay, what does distortion mean from a let's say data entry clerk? They can enter the wrong data. That's distortion. And how about delay? Hey, so and so, can you enter this paycheck thing into the system? Yeah, sure. After I go to lunch, right? So there's delay and distortion. Anytime you have a human in the middle of doing anything in a system, it's a connection domain, and they will insert distortion and delay, and you have to be able to understand or model what that is. Okay, so what does all this mean? First of all, it should be obvious what it means. You have to be able to understand your system well enough to be able to deal with these connection domains. So this picture, it's in your notes. I just drew it in a slightly different way, but you can see the application domain, the weather station connection domain, the network connection domain, the computer, which I left it off. This was the machine domain. Now, if you had a researcher that was required to enter information into that system, they could be considered another connection domain because of what I just said, right? Does that make sense? Okay. Now, so there we go. Your notes, I already talked through that. We're going to be talking about something called frame diagrams, and this is another way of describing all these, instead of putting this big Venn diagram together, there's a better way of doing it. You can do it this way. And so basically here are some very small number of key rules for connection domains. The machine domain, which is what the computer, that's always draw that in a double box like I have it here. And in that double box, you can just put at a very high level the name of whatever system you're developing. Trucking scheduling system. Just put that in there, okay? You always want to draw the domain, the application domain. The one we drew on the pad was the sun. That in this case where I was trying to get temperatures. That's one domain. That's the application domain, the real world. What were the connection domains? It was the weather station and the internet. So see how temperature, I don't have a direct connection to the information system. I had to go through weather station and the internet. Remember that picture? You can flip back through this in your notes. You can see how it's the exact same thing. And then what I added here was researchers, which I'm going to assume that the researchers interact with the machine domain. So I show that in this picture as well. Now, the only other thing you need to add when you're developing a frame diagram, so again, it has a machine, M, it has the application domain, it has any connection domains, and then any other, I'm going to call them domains of interest. In this case, the researchers are involved in this system, so I added them as well. Now, when you're developing a frame diagram, the only other thing you have to do is add this thing over here. This is called the requirements bubble. And the way, and this will become a little bit more obvious over the next 15 minutes, this is trying to show, and it's connected to the researchers here and temperatures, it's trying to connect or show the relationship between the primary domains of interest. So in this particular case, I can read this as the fundamental problem I'm trying to do here is the researchers are trying to query for temperatures. Okay? So there's different things to put in that requirements bubble. We're going to go through some examples. But you should be able to read it very nicely. Researchers are going to query for temperatures. Don't worry about the connection domains. They're just a side effect of the fact that I couldn't do it in an ideal sense. Fundamentally, what I'm trying to do is just query for temperatures. How I do it, I have to go through this other path, okay? That is a frame diagram, and fundamentally, that's what you're being asked to do with homework 3. Now let's talk about what a few of these different frame diagrams look like, okay? We'll wrap that up. Last topic for tonight, but very important because your homework 3 is based on it. So it'll take me no more than 20 minutes, and I'll let you go. Now, so far we good? Okay. All right, now there's different types of what I'm calling problem frames. I'd say almost every software system could be mapped into one of these types of problem frames. There's queries where people are going to be requesting information. That's called an information frame. I'll talk about examples of that. There are software systems where we have to describe behavioral rules where those rules will control something, like for example that trucking system, that trucking inventory system, or trucking, what I call a trucking scheduling system. That's a control problem. Why is it a control problem? Because I cause something to change in the environment. What am I causing to change in the environment? I'm causing trucks to go this way and that way and the other way, right? So it's causal, as opposed to a query, which is non-causal, doesn't change anything, I just query. And I'll go through each one of these. There's mappings, which is a transformation. There's a workpiece, and then we've already talked about a connection domain. I'm going to go through each one of these, show you what they look like, talk about a couple examples. You'll be good to go, okay? So let's start with information problems. We just talked about this with the research problem I just got through going through. A little bit more general. Here's the information system, the real world. The example we just talked about was temperatures, and this was the researchers, right? And that was the computer at SMU. Information requesters querying for information from some part of the real world. An example might be an inventory control system. Let me explain it to you. Let's say you want to build software that is an inventory control system for your store, like brick and mortar, like, jewelry store, whatever, a clothing store. That inventory control system, you want to be able to say from your computer, how many red sweaters do I have on the showroom floor? And you should be able to query your computer and get exactly how many red sweaters there are on out on the show floor, right? Now, do you actually go out there and count the red sweaters? No. It's in the system. You just query and it tells you. Now, the system should reflect the real world, but that's not that's part of how you solve the problem. You're just querying for whatever red sweaters, jeans, whatever you're trying to query for. So it answers queries about the real world. In this case, the real world is your clothing store that people are walking around and looking at stuff. So the key challenge is, how does the software get access to that? The key requirement is to satisfy the queries by these guys. What kind of queries do they want to make, how timely, et cetera. And the system is going to report on the state of the real world, how many red sweaters are on the showroom floor. The system doesn't change how many red sweaters there are on the showroom. It just reflects real world, just like reading temperatures, okay? So the inventory control systems are about modeling the real world. Now that can be static or dynamic. What does that mean? That means, static means when I want to learn how many red sweaters there are, I'm going to go read. I'm sorry, I'm jumping ahead. Passive or active. If it's active, it means I'm going to go read when I want to. If passive. Active means, an example. Okay, if you've ever had real-time stock exchange quotes coming to you, that's an example of something being more active, right? So you don't read it, it gets pumped to you. See the difference? Okay. The other thing about inventory control systems is how do they get updated? Let's say your red sweaters go down to 1 and you want to restock them. How does that happen? Does it happen when the truck shows up and it gets unloaded? How do you go from 1 left to 100? Those issues have to be worked with information problems, but it's all about, again, just reflecting what's happening in the real world. Does that make sense? Okay, I can either go out and ask, or I can be told. Okay, but I'm not changing anything in the real world. I'm just monitoring it, essentially. Okay, that's an information problem. Okay, so anytime this is key. Anytime the key problem is just being able to find out what's out there, querying for what's in the real world, that's the information problem, and you can usually model it like this, and then all it takes is you filling in what's in those boxes. What is the real world? What exactly are you querying for? You should be able to do that if you have a good understanding of the problem. Okay. A control problem. Okay, let me give you an example of a control problem. Let's say you're designing a system for call it FedEx, or even maybe the truck shipping company, or even the trucking problem I showed you earlier. And what happens here is, when a truck shows up, I'm describing a problem to you. Tell me if it fits into a control problem. The truck pulls into the warehouse. It's truck number 567. You type that into the computer, and the computer tells you, take the boxes out of truck 567 and bring them to loading dock D. Okay? What's happening there? The computer is kind of it's controlling something. What's it controlling? It's controlling where to take boxes off of a truck and where to put them. Okay? Now, how does it do it? Well, it may tell This control domain will be the actual trucks coming into the warehouse. The way it does it will vary. It could be some automated message getting sent to the truck. What if it's telling the person at the computer, hey, go tell Joe to go move the boxes from 567 to loading dock D? There might be right here, there might be a connection domain, it might be a user. And of course, we know what happens. They can tell them to bring it to the wrong dock. So that we know about the issues with the human. But this is different than an information problem where all you're doing is reading, you're monitoring. This is you're actually telling someone to go do something. So it's causal. It's causation. I'm causing a change in the real world. Hey, Mr. Truck Driver, there's a storm to your right. Take a left. Okay, real world actually changes. Causation. Does that make sense? Causation, something's really changing? Yeah.
So, I mean, it's giving information, it's not doing the thing.
It's not actually doing the thing. It's giving information and expecting the control domain to react. So
my question is like, what basically control domain is like, if you use a query and lose the stuff, like this is a from over there, without notifying, it takes away, I mean, at the same time.
Yeah. Okay, so there's a couple different ways of looking at it. Like, for example, remember earlier I talked about software that would control the motor on a refrigerator for cooling? That would be kind of like this. The computer controlling this control domain is the motor. There's no connection domain because it's the direct connection. You could add one if there was a interesting hardware mechanism in there that he had but anyway, that's an example of a human not in the loop. You could have to go through some other set of steps. It could be, you know what, you have to print out a report and the report gets looked at by a human and then towed to their subordinate. I mean, you can have all kinds of connection domains in here. It depends on how direct that connection is, and it'll vary by what kind of application you're building, right? So it could, so you're right. I mean, it could be direct control, it could be indirect control. That's all for you to figure out what goes in here. By the way, every one of these little pictures in these different problems, I'm not showing connection domains. They can get inserted anywhere in any one of these, right? Like I showed in the previous example. So again, so this is causing something to happen. What does it cause to happen? You have to define those in the rules. That's part of the requirements, okay? So control, you're causing something to behave in the real world or the application domain. Does that make sense? Okay. Okay, transformation problem. Now this one, again, let me give you an example. Sometimes the example is better to say first, and you can understand it, all the wording here. Let's say you've got a picture, a hard copy picture that your grandmother gave you many years ago, and it's, you know what, it's kind of old and yellow, and it's got all kinds of, scratches in it, and you want to enhance that picture, and you found out that you can go buy some picture enhancement software, and you can run your picture through this software, and it'll make it look really, really good. Okay? You say, okay, I want to go do that. So you go out and you buy some software. You load that software on your computer, and you take that input image, and you run it through this algorithm that cleans it up, filters it, transforms it, and you end up with a better picture over here. That's an example of a transformation problem. And the real requirement is whatever, I call it mapping. It's a very general term, but think of mapping as whatever transformation you want to have done from input data mapped to output data. Now that mapping could be image enhancement software. It could be whatever is taking one and producing the other, right? See what I'm saying? So anytime I'm taking, okay, here's another example. You go to the grocery store, you pick up a product, and you want to go pay for that product, okay? What's on the thing that you bought at the grocery store? It's a barcode. And you take that barcode up to the cashier, and they swipe that barcode, and what gets produced? So a cost or something like that, or a product ID number. It depends on what you're trying. So that, barcode to product SKU or whatever. Okay, that's another example. Anytime I'm transforming one thing to another thing, Many problems are like this. That's a transformation problem. So the key challenge here is really describing what that mapping rule is. So you have to look at all possible inputs, map those to all possible outputs, which essentially can be done with an algorithm, image processing algorithm, what have you. But that's how this kind of problem works. I'm taking one thing, just transforming it to another thing. Device drivers can work this way. You take a command, you convert it to a signal, the device driver. These things work this way, okay? So transformation problem. Okay, workpiece problem. This one's a little bit interesting, but it's actually very, very simple. Okay, when I created this PowerPoint presentation and I saved it, where did it save it? Saved it in my computer, right? Okay. A workpiece problem is anything where when I produce a workpiece, like a PowerPoint presentation, it gets stored in that. That little dot means that this workpiece is stored inside the computer. Okay? So this means anything where what I produce, it could be a PowerPoint file, it could be a CAD drawing, anything where what I produce resides in my computer is called a workpiece problem. Now, can that thing that resides inside my computer ever get printed out? Sure. You can print out a hard copy, send it, do whatever you want with it, but it primarily exists within my computer. Okay? That's what that little nomenclature means, okay? So software serves as a tool for creating objects, PowerPoint, CAD drawing, Excel, whatever, in my computer. Now, what is the key software challenge when I'm producing PowerPoint slides? Well, it's almost all user interface design. PowerPoint is all user interface design, right? So the majority of the work for workpiece problems, the software requirements, are in user interface design. And then the majority is just programming that up and creating the files, et cetera. But most of the requirements are going to be around what are the functions you want to let your user perform to create this workpiece, and almost all of that is going to be user interface design, right? There's no like image processing algorithms and stuff like that. It's all just user interface design as far as the application you're building, right? Okay? And then we already talked about a connection domain, connection problem, which could really exist anywhere within those other problems I just talked to you about, right? I mean, even back over here, this, in a sense, the user could be, in a sense, a connection domain, right? Because they can type in the wrong commands and do the wrong things, okay? But okay, so we know what a connection domain is. So, we have. So let's summarize because we're going to stop here. We have multiple different types of problem frames or problem types, right? And I would say a large majority of any software system you're going to be working on will consist of one or more, because your system can actually have more than one of those problem frames that make up the system. But it'll be a combination of these different problem types. So we talked about information problems. All I'm going to do is read and query, not change anything. Control problems, I'm going to actually cause something in the real world to change, trucks turning and all this other stuff. Transformation, convert one thing to another thing, right? Workpiece, creating computer files, think of it that way, you know, and then all the associated user interface design that goes along with that. And then one thing that permeates all of them, that tends to exist everywhere, is connection domains, which you'll have one or more of them in almost every problem, okay? So having said that, any questions on any of that? So having said that, let's briefly talk about the homework, which I know you're dying to get to. Problem framing. Okay, so I'm going to ask you to do three problem frames for your homework. And the three are a traffic light controller. So think of a traffic light in a busy intersection. You've all seen them. If you were to describe the problem, to develop a problem frame for a traffic light, I'll come back to that in a second. A program that tells a bus rider which buses to take to get from one location to another. And then thirdly, an electronic email system. Now, I'll tell you, the types of problems that we just talked about, one of those will apply to each of these. I won't say that one of these three won't maybe have more than one problem frame, but they'll have at least one, and I think every one of them is going to have at least one connection domain. Okay? Now, so what I want you to do is the following. Draw the frame diagram. You saw the blocks and the connections in the notes. I showed you an example for every type of problem frame. Identify any connection domains, which I said there'll probably be at least one. And then for each connection domain, you have to go a little bit further. Remember what we said that each connection domain implied? It's going to always set an upper bound on how well you can do, and it's going to insert distortion and delay into the system. I want you to tell me what you think that distortion and delay is. You don't have to obviously tell me exactly what the quantitative, just tell me, what it is. Like, the internet, the delay is going to be how long it takes to go through the network, things like that. So you don't have to be very specific. Just tell me what you think, where the distortion and delay comes from. And do that for each of these three. Let's think about traffic light controller. Okay, so let's just talk about that one for a second. So first of all, what might be the application domain, the domain of interest? What might that be? How would you describe that? So the way I kind of view it is, picture yourself in the real world. And in the real world, if I'm sitting at a traffic light, what is the real world? Here's how again, I'm just going to throw out some ideas. But if it was me, I would probably think that, I would almost visualize myself in a car at an intersection, right? And there's some kind of traffic light here, and there's cars lined up and things like that, right? I'd probably that's kind of the real world, right? In which your traffic light might exist, and so I would maybe think about describing the real world in that context, right? Would you agree? That's what we sometimes refer to as the application domain. When we write our requirements for the traffic light, we write them in terms of this, right? What's happening out here, okay? Now, how would you actually just, what would be maybe the machine domain? So it could be a couple things. Again, it could be the traffic light, right? Red, yellow, green. It could be that hanging there. Maybe you want to think about it. It's over here on the light pole where it's got the control system running, running the software that's telling the traffic lights what to do. Because remember, the traffic lights, they look this way, they look that way, this way, that way. Okay, well, you think about that. What kind of problem might this be? We know we have information problems, control problems, transformation problems, work piece problems, and then connection domains. And remember, again, we said that over here, you're mainly just, this is just a query. This is your controlling. So over here, nothing in the real world ever changes at all. It just continues to just be. Over here, you're actually going to make stuff happen. Over here, you're going to literally go through a transformation of one thing to another. Work piece, okay, it's something that it's never going to leave the computer. You know, which of those might it be? Maybe. What are you controlling?
Well, kind of the light is controlling which way you have to go, or you should stop or break, or it's kind of information as well because it's giving you an information if you have to go, if you can't go.
Well, okay, that's a good point. I think, but here, remember, information is just, the system is just querying what's going on in the real world. It's not providing information to the real world. It's getting information from the real world. Controlling, you're actually making things happen in the real world. Can you see what you might be making happen over here? What are you making happen over here in a control problem? Yeah, think about it as generally as possible. If you're making cars stop and go, you're controlling the real world, right? It's causal. You're making things. Yes, cars can disobey though, but you're essentially controlling the real world. Information problem is you're not supplying information to the real world. You're reading information from the real world. It's more of a read, not a write. If that makes so, you actually hit on it. It's probably more of a control problem, right? But think about all of them and see whether there might be some other types of problems mixed in. And then think about maybe is there a connection domain? You know, right? I mean, there could be different connection domains. Some people get innovative with this, but I'll give you one example. Sometimes, you know, if cars want to turn left, they actually go on a pad, which sends a signal to the light to do something. And you know, there's a path by which signal. You know, think about different ways of maybe weaving in some connection domains into the problem. Okay, I'm not going to give the whole answer away, but you guys seem to have that. That's kind of what I'm looking for, right? But again, so identify which, you know, do that for all three. Describe distortion delays. These things are meant to be general. If you draw a block diagram of the system, you get it all wrong. It's not a block diagram. The only thing you're representing as far as your application is that one computer domain, M. Everything else is the real world. So if you draw a block diagram, you're fundamentally off on the wrong path. So think about that. Think about just the domains. Don't draw me a block diagram. It looks like a block diagram but it's actually the only part that your whole system at this point in time is that one double box where it says M. Okay? That's it for tonight. Your homework 3 is going to be based on this. This homework, because problem frames are a little bit different, you know, I know it's new material, and sometimes people take a little bit longer on it because it's kind of abstract thinking. But it's very important because what allows you to do is discover hidden requirements and restrictions. I told you about all those accidents and stuff that happened because we didn't properly understand the domain and the environment. This allows you to think more about that, and usually it uncovers hidden requirements. What's a hidden requirement? Anytime you have a connection domain where you have to identify distortion and delay, you're getting into the details where it wasn't obvious when you were describing it. So that's why we're doing this. All right, guys, have a good week, and I'll see you back again next week, same time.
Okay, so can it be information domain?